record. Okay, we're back, and with a smile. Okay, and let me share my screen here. Okay, so I copied the Jacobian matrix that we just discussed so that we can use it as our stepping stone for the discussion. And this is the robot, the wrist robot. This is the physical, the drawing of the robot. And we concentrate on what is the values of the forward kinematics as well as the Jacobian for us to determine how we are going to compute. So now, here, let me just write it down here. Okay, so we'll compute here. So first we have a Jacobian matrix already. And then what we need to do is to compare the step size. To compare what is your desired values of your x desired and your x desired in terms of position and and your actual x position. Okay. Now I think I need another. Did I show it here? Well, it's already here. I need another slide to show me this one, the orientation. Okay, anyway, maybe we can do it from here. Okay, so I want another slide. Okay, let me see if I can get another. It doesn't open a new window. Anyway, so it's here. Okay, so very good. I want a new window for me to show the error terms there. These are the error terms that we need to compute. Okay. Okay, now let's start. So all we need, okay, we want to compute. Okay, for example, we have an initial joint values. Okay, let's assume that we have initial joint values of Q. So we have Q. Okay. We have Q. Okay, which is equal to Q1, Q2, Q3, or the way we say it is theta 1, theta 2, and theta 3. So theta 1, okay, there. So now we initialize. Let's say, for example, just for easy discussion, we put our initial values at 0. Okay, then we set our desired. So we have our values there, our desired, x desired. Okay, your x desired is composed of two things. Yeah, desired position desired, as well as a certain kind of orientation desired. Okay, let's start with position first. So we say our desired position, PD, let's just say that it is 1, 1, 1. 1, 1, 1. Okay, that means that in your here, Okay, somewhere in your, okay, for this one, the base reference frame is coincident with that one. So we say that your Z0, Z0, maybe Z0 is somewhere here. Okay, that's the rotation. Okay, then here maybe X0 and Y0. Okay, so if we say our desired value of 1, 1, 1, so 1 in terms of X, 1, okay, maybe this is 1 in terms of X, and 1 in terms of Y, and 1 in terms of Z. So we can say like this and like this. So we say here, somewhere here, and it goes up to here. Okay, so your N effector will be somewhere here. That's 1, 1, 1. That's where we want our N effector to be. That is the hand of the robot will move there. Okay, so now that's 1, 1, 1. Now, what is our desired orientation? We have to be careful because when we say desired orientation, I just put it phi d, but when we say, because this is in a vector form, now if we say desired orientation, we have to consider that in our discussion here, we want to consider the desired rotation matrix. Okay, so now this desired rotation matrix has xd, okay, because here it's similar, so we try to avoid using that, xd, yd, and zd. Okay, so for us to avoid confusion, we call it NOA. And the first column, the next column is O, desired, and A, desired. Okay, that's all to denote the columns of the rotation matrix. Okay, so now, of course, if you have a rotation desired, then we'll have a rotation that is the actual orientation. So now you have N, O, and A without the subscript. Okay, that's the actual value. So for us to compute the error term, we are going to consider this error in terms of position. The desired position is 1, 1, 1. Actual position is computed using the rotation, using the transformation matrix. Okay, and then the desired orientation. Okay, against the desired orientation against actual orientation. Okay, let's start so that it will be much clearer for you. So our Jacobian is this one. So we say that the initial value of our angle is 0. So we can put 0. Many of these terms will become 0. Okay, so let's start. Let's start first with what is the value of your Jacobian. Where is the rotation? Okay, so your Jacobian will be okay. So sine of 0, that's 0. So this term is 0. Whenever there's a sign, everything will be 0. So this one is 0, 0, 0, 0, 0, 1. That's the first column. Okay. Second column, cosine. This is cosine. So that's 0. That is 1. Yeah. So this is D3. Next, there's a sign. That's 0. Okay. Whenever this a sign, that will be 0. So that's 0 and 0. Next, that is 0. And that is 1 and 0. Next, anything with a sign, that's a 0. If there's a sign, that's a 0 again. There's a sign here. That's a sign. That's a 0. Okay. What about this one? There's also a sign. That's a sign. So that's 0, 0. And the last one is 1. There you go. That's your Jacobian. Okay. Okay. So we say we take the Jacobian inverse. Okay. For our discussion here, okay, because this is a large matrix, we cannot, it's impossible to take the inverse of that. Okay. If we consider only the position, that means we cut the Jacobian up to here, only take the first part, then we can take the inverse of that. Okay. But if we consider the orientation, yeah, it will be a very complex computation. So let's consider in terms of inverse, we use the Jacobian transpose instead. Just transpose that just for computation. And then your KP is, we need to know, okay, your initial value is this one, yeah? So that means your Q, we want to compute the new Q, okay? Given your Q, the new Q at the first step, given your Q at the 0th step, plus the delta of the Q, where the delta of the Q is computed using the Jacobian transpose, okay? So here, this is, of course, we know that this is 0, 0, 0, okay, plus your J transpose, which is the transpose of this, multiplied by KP. Our KP is set to 0.1. And then your error, the error in terms of the position, okay? So now you have the desired value. So the desired of the error is desired of the position is 1, 1, 1, okay? Minus, what is this now? The position, which is, of course, 0, P3, yeah? The position of the end effector with respect to the base. So what is 0, P3? Okay, it's here. This part, that is 0, P3. Okay, so we say, okay, we annotate. Okay, 0, P3. So this is, what is that? This one. So we say that whenever there's a sign, it's a 0. So that's 0, 0. So 0, 0. And then now this is 1. And this is D3. So that's D3. Okay, there. Okay, now what is your rotation? Okay, our rotation. Okay, I think this one I don't need. I can put let me cover this part so that I can use it to write my things. Okay. So we continue from up here. Now, this is your Q. We want to compute what is the error in terms of the orientation. So the position error, okay, let me just write it again so that it will be clear for you. So there is okay, this part. The error in the position minus, okay, this is the one that we are trying to compute. The error in the position and the error in the orientation. So the error in the position, we already know. So error in the position is equal to 1, 1, 1 minus 0, 0, D3 is not stated on what it is. Well, we can assume it to be, let's just assume D3 to be 0.3. Okay, then you can have your error in the position already. Okay, now our question is error in the orientation. Error in the orientation. Okay, so we know the 0, we know the 0R3. So this one will be the error in the position is a function of, okay, 0R3 and the desired rotation. Okay. Okay, what is our desired rotation? For example, we say that we want our n effector to be 90 degrees. It rotated 90 degrees about the z-axis. Okay, so that means that, okay, if we want our rotation, okay, for example, this has rotated 90 degrees about the z-axis. So what is rotation of z by 90 degrees? So we say, okay, okay, so we can set our rotation desired. Okay, 90 degrees about the z-axis. Okay, so what is that around z-axis? So z-axis is 0, 0, 1, 0, 0, cosine of theta, whatever that angle is, cosine of theta, sine of theta, and minus sine of theta. Is that correct? Where's the negative sign? Is it a negative sign there? Okay, let me check. So the rotation about the z-axis, okay, the negative is on the other side. So the negative is here. Okay, let's erase this negative. The negative is on top. The negative sign is there. Okay, so if we say 90 degrees, our desired rotation is 90 degrees. Say 90 degrees about the z-axis. About the z-axis. So 90 degrees about the z-axis, cosine is 0. So everything here is 0. So this is 0, diagonal term is 0. Again, this is 0, 0, 1, 0, 0. Okay. Then what about here? When you say sine of 90 degrees, that's a 1. So here, minus 1. Okay, and this is 1. Okay, so that is now your desired rotation. So now you have, we say that the first column is your N desired. The next column is your O desired. And the third column is your A desired. Okay, so these vectors are, this vector is that vector. The next vector is that vector. Okay, the next one is this. Okay. Okay. Then what about your actual rotation? So what is your 0R3? So your 0R3 is computed from the transformation matrix, of course, which is computed from 0A3. where your 0R3 is this part of the rotation. Okay, so because we say that everything is zero value, so anything with a sign is zero. So this is 1. First part is 1 minus 0. That's 0. That's 0. So this is 0. This is 0. Next, anything with a sign is 0. Anything with a sign is 0, but this is no sign, so that's a 1. And sine 0. Cosine, sine 0, so 0, 0, 1. There you go. Okay, so now what is your error term now for the orientation? So we check how is the orientation error computed. Orientation error is computed by crossing. Okay, cross product. Where should I go? I'm running out of space. Okay, I will look at it later. For now, I will increase here. Okay. It's the biggest challenge of online teaching. No space, difficult to write. There. So now, what is your error term? So your error of orientation is equal to that one. 1/2 of what is your NA? NA is the actual N. Okay. So the actual N is this one. So this is NOA. Okay. So that is N. So that's the 1, 0. Sorry. 1, 0, 0. This is 1. Yeah. Cross with what is the desired? N desired. N desired is this one. 0, 1, 0. Plus O actual. O, this one. 0, 1, 0. Cross with O desired. O desired is this one. Minus 1, 0, 0. Plus A actual. A actual is this. 0, 0, 1. Cross with A desired. 0, 0, 1. Okay. Okay. Now, if we use the same S parameter, I mean the skew symmetric matrix, so that it will be easier for us to see. So you have 1/2. Let's just do that. So now multiplying with the skew symmetric matrix, that's 0, 0, 0. And this is the first component. So the third component and the second component is 0. Third component and second component is 0. This is minus 1 and 1. Multiplied by 0, 1, 0. Do you remember that? The skew symmetric matrix? Okay, let me write down here somewhere so that you can remember. Skew symmetric matrix of A is equal to 0, 0, 0 minus A3, A2 minus A1, A3 minus A2 and A1. Okay, there. Okay, that's what we use here. So plus, next. Okay, so again, 0, 0, 0. And this is the second component. Third component is here. First component is here. And the second component in this part. So this is positive 1 and negative 1. Okay, multiplied by minus 1, 0, 0 plus. Again, we skew symmetric matrix. This one, 0, 0, 1. So skew symmetrics, diagonals are 0. And then only the third element has a 1. So the third element minus 1 here and 1 there. The rest is 0, 0, 0, 0, 0. And 0, 0, 1. Now we can compute everything is equal to 1/2 of what is this vector now? The first vector is 0, 0, 0, 0, 0, 0, negative 1. So 0 minus 1 and 0. That's the first vector. Plus, any questions? 0, 0, 0, 0, 0, 0, 0, 0, 0. Oh, no, that's wrong. 0, 0, 0, 0, 0, 0. 0 is the third one. 1. That is 0 and this is 1. Okay, 0, 0, 0, 0, 0, 0, 0, 1, 0. Yes. Next, 0, 0, 0, 0, 0, 0, 1. So positive 1, 0, 0. It's positive 1. Only in the third element, you have a 1. Just a positive 1. Okay, sorry. Plus, now, 0, 0, 0, 0, 0, 0, 0, 0, 0. You see it? 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so you add. So this is 1/2 of, what is that? The result is 0, 0, 2. So the result is 0, 0, 1. Okay, that's the error term. I mean, that's the error in terms of the error term of the orientation. So here, the error term of the position EP, okay, let's just write the number of the EP. EP is 1, 1, and if this is 0.3, so 1 minus 0.3, that's 0.7. So 1, 1, 0.7. So now we can write here. So let's erase some here because we know the values of this. So now, okay, here it will be 1, 1, 0.7. And that's the error or the position. Error of the orientation is 0, 0, 1. Finish. So what is that? We can compute. Okay. So this is 0.3. Okay. So if you transpose, so that means that the first row multiplied by this one. So 0, 0, okay, 0, 0, 0, 1. Okay. The first element is a 1. Next, because we are going to transpose 0.3, okay, 0.3 times 1, so that's 0.3, plus 0, plus 0, plus 0, plus 0, plus 0. So this is 0.3. Okay. Only this part. Sorry. No. Let me be careful of. Be very careful in writing so that you will get. You can see this one. Oh, when I upload the video, that's 0, 0. Plus, we are going to multiply this one. I'll put the 0.1 first so that, you know, the KP. Then the result of the J transpose times that one, it was 1 and 0.3, I think. And then the next one, 0, okay, 0, all 0 until a 1. There you go. Okay, so that means that your new angle now is what? Your new angle is, this is times 0.1. So your new angle is, let me, it's very difficult to, okay, this new angle Q1, okay, so your new angle in the first step, Q1, is equal to, now, 0, 0 plus 0.1 of that. So now this is 0.1, 0.03, and 0.1. There you go. So, and this is in terms of radians, okay? So you step in terms of those radians. That will be your new value, okay? Then you substitute now. You repeat the process. To repeat the process, you have to go back to the Jacobian again, Jacobian, and key in the values of J. After the J, you compute the error terms of the position and the orientation, checking the one that changes here. The desired values don't change, only the actual values change. That means that your value of this part, you have to compute what is the new angle, okay? Theta 1, theta 1, theta 2, and theta 3, okay? So what is your position value? You can compute from here. D3, we assume to be 0.3, and you can compute that as well as the rotation matrix. So now you will be able to define your rotation angle, I mean the rotation matrix 0R3 based on this value, new values of the angle, and your 0P3 based on also new values of the angle. And that's the only one that changed, including the value of the Jacobian. And then you compute the new value. So in your new step now, it will be like, let me just, okay, you have done this in machine learning. So you have Q, next step, Q2, okay, will be that one. Your Q1, that is this one now, 0.1, 0.03, 0.1, okay, plus your KP times J transpose times again your error in the position and error in the orientation. Okay, that's your next angle. And to compute for the error in the position, this is, you follow the same procedure of your desired minus the actual position, and then the error in the orientation. You know your 0R3, which will be based on how your joint moves, and then your R desired remains the same, which is this one. We assign our R desired to be 90 degrees rotation about the Z axis. Okay, if you run this in MATLAB, you can see how the position and the orientation change as you step into the computation. Any questions? It's 1 o'clock already. Sorry, I exceeded the time. Okay. Feel free to ask questions if I can answer you. You can also ask the, if I'm busy, you can ask the Ms. Camela. if you want some clarification. Questions? It's 1 o'clock already. I will upload the video so that you will be guided in terms of answering your assignment and see if it can help you. Okay, it's just a matter of substitution, checking, all the algorithm is there and just looking at the right term to substitute into the equations. If you know where to find them, well, you know where to find them. It is just in the transformation matrix A. That's all. Take the rotation part and take the position part. Finish. That's it, and then do the computation. Okay, so with that, you will be able to move any robot in full dimensional space in terms of position and orientation. Congratulations. Okay, okay. Thank you, guys. And then I will wait for your submissions, and then see you on Friday for your long test 2. Please study. Okay? Okay. See you. Bye.